So we'll continue the video with the second part where we will talk about the operations of power series. So there are three permissible operations on power series, which are differentiation, addition, and multiplication. So first we'll have a look at the term-wise differentiation. Okay, so the power series may be differentiated term by term. So now you're given the y of x equal to this power series. So because you know, just remember, always remember that the end goal of learning about power series here is to find the solution to ODE. So y of x here is, let's say, the proposed solution to a given ODE. So this y of x is expressed as a power series of this standard form. Summation from n equals to 0 to infinity of a sub n times x minus x naught to the power of n. And let's say this series converges for x minus x naught less than r, where the value of r is greater than 0. So from this y, you can get the y prime, i.e. the dy dx, equal to this term. So notice the difference in the starting point of the series. So for yx, you start from n equals to 0, but for y prime of x, you start from n equals to 1 until infinity, and then n times an, and here you got n minus 1 as the index for the variable x minus x naught. And then you can also differentiate again term by term to get the second derivative of the yx. So you get y double prime x. Now the power series starts at n equals to 2. Okay, not n equals to 0 or 1, but n equals to 2. And then n times n minus 1 times a sub n multiply with x minus x naught to the power of n minus 2. So I'm going to show you how do we get to this point that such that y prime starts from n equals to 1 and y double prime starts from n equals to 2. So let's go to the whiteboard. Hopefully it works this time. So okay, now you have this y of x equals to this term. So we can expand this y of x for several terms. Okay, so start from n equals to 0. So you have a naught x minus x naught to the power of 0 plus a1 x minus x naught to the power of 1 plus a2 x minus x naught to the power of 2, and I will stop until a3. Don't worry, I'm not going to go on, and plus so on and so on. Okay, so let's further simplify this. So this is a naught plus a1 times x minus x naught plus a2 times x minus x naught square plus a3 times x minus x naught cube plus and so on and so on. Right, so now let's differentiate this dy dx. So y prime x or dy dx equals to, so the first term is 0 because there isn't any x here, so we can start with a1. So differentiate this, you get a1 plus, okay, now you differentiate this term, you got a2, and then you bring the 2 in front, and then you get x minus x naught. That since x here is just x, so you don't need to differentiate. I mean, even if you differentiate that, you get 1. So okay, and then for the next term, you got you bring 3 in front, so you get 3 a3 times x minus x naught to the power of 2, and so on and so on. So you can see the trend here, right? So now if you you see the pattern, it starts from a1, and then you get 2 times a2, and then here is 1, then 3 times a3, here is 2. So then you can summarize that the first derivative of yx is thus the summation starting from n equals to 1 until infinity of n times an x minus x naught times n minus 1. Okay, so that's why for first derivative of y prime, it starts with n equals to 1. It doesn't start with n equals to 0. Okay, so and then you can do the same here. So we start from this term to get the second derivative of y. So y double prime x. So from that term, so you differentiate a1, you get 0. So just 0. So we start with the term, this one. Okay, so you get 2a2, just 2a2 plus 3a3 times 2 x minus x naught. And if you want to convince yourself, you can go on and on to get 4a4 times 3 x minus x naught squared, and so on until infinity. So you can see that for the second derivative of y of x, so it starts with a2. You don't have a0 and a1, so that's why the second derivative of y starts from n equals to 2 until infinity of n times n minus 1 a sub n times x minus x naught, now to the power of n minus 2. Okay, so you can also have it, you can get to this point just by looking at the original y of x here. So you can just, differentiate the first derivative to get n x minus x naught n minus 1. It's just that you need to know that it starts from n equals to 1. Okay, and for the second derivative of this one, okay, so just from this term you can just you just bring n time, and then you bring n minus 1 in front, a sub n x minus x naught, and then n minus 1 is n minus 2, but then you need to know that it is starting from n equals to 2. Okay, so that's the first operation of power series. So it can be differentiated term by term, and you need to be careful. We're going to use this a lot to solve for the ODE. So y is this, and then y prime is this, and then y double prime is this whole thing here. Okay. Okay, so let's go to the next operation of power series. So the next operation is the power series can be added term-wise. So let's say you have two power series. You can add them term by term. Let's say you have these two series here. So one series starts from n equals to 0, a sub n x minus x naught to the power of n. And the second series is b sub n, starting from also n equals to 0 to infinity, x minus x naught to the power of n. And these power series have positive radii of convergence, and their sum are fx and gx. So here, this is your fx, and this is your gx. Okay, and then you can just simply add them together. Okay, if you want, you can also convince yourself and try to expand those terms. Okay, so the first series you have is from n equals to 0 to infinity, a sub n x minus x naught to the power of n plus n equals to 0, b sub n x minus x naught to the power of n. So when you expand each term, so you have a naught plus a1 x minus x naught n, no, just 1, plus a2 x minus x naught squared, and so on and so on. And then plus with the second series, so this is the first series, plus with the b series, so you get b naught plus b1 x minus x naught plus b2 x minus x naught squared, and so on and so on. So you can just collect all the similar terms together. A naught, b naught plus a naught, a1, b1, a1, b1, x minus x naught plus a2 plus b2, right? X minus x naught squared, and so on and so on. Thus, this can be simplified to the summation from n equals to 0 to infinity of a sub n plus b sub n times x minus x naught to the power of n. Okay, so that's what we meant by the term-wise addition of the power series. You can add them term by term. Okay, so that is the second operation you can do with power series. So the next operation that you can do with power series is the term-wise multiplication. So the power series may be multiplied term by term. So suppose that you have these two power series A and B starting at the same point, n equals to 0 for both, and both variables have the same indices, x minus x naught to the power of n. So let's say both series have positive radii of convergence, and this is your f of x and this is your g of x. And the series obtained by multiplying fx and gx term by term, then you can do this, or you can convince yourself again, like what I did in differentiation and addition. So, but it's a bit tedious for multiplication, because when you expand something, then it's tedious. Okay, let's just do that. Okay, so you have this first series from n equals to 0 to infinity of a sub n x minus x naught, and now you want to multiply with the second series, b series, b sub n x minus x naught, and so you can expand a little bit until, let's say, so you expand from n equals to 0 to n equals to 2 only, okay? So a1 times x minus x naught plus a2 times x minus x naught, the whole thing squared, plus so on and so on. So you stop the series and then you start with the second series. You have b naught plus b1 times x minus x naught plus b2 x minus x naught squared, plus so on and so on until infinity. So here, when you multiply the series, you have to be careful because you need to expand it term by term. So this a naught multiply b naught, this a naught still multiply with this b1 term, this same a naught will multiply with this b2 term. So, and then you get a naught b naught plus a naught b1 x minus x naught, and then plus a naught b2 x minus x naught squared, okay, and so on until a naught b3, a naught b4, and so on and so on. Plus, then you multiply the second term. So now you get the term a1. So a1 times b naught term, a1 times the b1 term, and a1 times the b2 term, and so on, so on. So you can see that where things are heading now. So looking back at the PowerPoint slide, so you can simplify that if you multiply this fx and gx, then you get this, something like this, okay? So the series will start from n equals to 0 until infinity. So a naught times bn plus a1 times bn minus 1, and plus and plus and plus, multiply with x minus x naught to the power of n. So this n starting from 0. So you see that when you expand this series, you will get what we have been trying to work out in the whiteboard just now. Okay. So this series converges and represents fx gx, fx times gx for each x in the interior of the convergence interval of each of the given series. So just remember, in short, the operations of power series can be differentiated term by term, it can be added term by term, and it can be multiplied term by term. So it doesn't say that it can be divided. So just let's just stick with those operations for now. Right, the other property of power series that is useful is this vanishing of all coefficients. So this is a condition that is a basic tool for the power series method. So what does it mean by vanishing all coefficients? So let's say if you have a power series that has a positive radius of convergence and a sum that is identically 0 throughout its interval of convergence, then each coefficient of the series is 0. Okay, like if you add all the power series together and everything equals to 0, then it must be that the coefficients of the series is 0 in some ways, because x cannot be 0 and x not necessarily be equal to 0. So we will, it's this vanishing of all coefficient is comparable to the comparing the coefficient, in partial fraction and in method of undetermined coefficient, where you have left hand side and right hand side. So when you have the coefficient at the left hand side, you want to compare with the coefficient on the right hand side. And in this case, the coefficient on the right hand side are all equals to 0. So then we work out what are the actual values of the coefficients. We don't mean that everything is equal to 0, but then this property is useful when we equate all the coefficient equal to 0, then we can find out, the actual value of the coefficient. Okay, so the next property is shifting summation index, summation indices. So indices are and it is the plural of index. Okay, just reminding myself. Okay, so an index of summation is a dummy and can be changed. Okay, so there's this typo here. So this shouldn't be 1 and 18. It should be 3 and I don't know, something. If you 3 squared plus times 2 squared over 2 factorial, whatever you get is this value here. So it's a bit of calculation error. So these two terms are wrong, but the third term and maybe the next ongoing terms are correct. Okay, so here, so let's say you have this series here. So the summation from n equals to 1 until infinity of 3 to the power of n times n squared divided by n factorial. So this n here, you can just substitute with any other letters. You have 25 letters in the alphabets. So you can substitute in this case with k. So if you just put n and with k, then everything is in terms of k. So that's just a, just a property so that you're not confused. So it's a dummy and can be changed. So in this case, if you put k equals to 1, because this series starts from 1, then you have 3 to the power of 1, 1 to the square over 1 factorial. So you get 3 plus the second term should be this one. So you get 9 times 4 divided by 2. So you get 18. Correct lah. Okay, 18. And then this third term is 3 cubed and then 3 squared over 3 factorial. So 3 factorial is 3 times 2. So then you get 27 times 3 is 81 over 2, and so on and so on, and as your k becomes 1, 2, 3 until infinity. Okay, so yeah, it's a dummy and you can change from n to m to k, whatever. And then another property is the shifting of index. Index of the summation can be shifted, i.e., let's say you have this series here. Okay, let's say you have the series where it starts from n equals to 2. Well, you can see that this is the second derivative of y, right, from the original y series. So here, series starts from n equals to 2, but let's say we set the n equals to s plus 2, and then from this, you know that s equals to n minus 2. So what we want to do here is we want to make the series starts from 0. So we want to shift the index of the summation. So we want to shift it, so we need to do this substitution. So let's say substitute n with s plus 2 and s is n minus 2. So now instead of starting from n equals to 2, now you want to start from s equals to 0 until infinity, because s is n minus 2. So when n equals to 2, 2 minus 2 is 0. So s equals to 0. So here your n is what? N is s plus 2. So n is s plus 2. So put this as s plus 2. And then here your n is still s plus 2. So s plus 2 minus 1 is s plus 1 now. And then your a sub n. So n here is still s plus 2. And then x minus x naught. So n minus 2 is just s. So put there s. So now you have shifted the index of your series to starting from 0, and now your index is now just s. no longer n minus 2. And remember the previous property that the index of summation is just a dummy and can be changed. So you can also rewrite this series if you want it to be maintained at using n. So it starts from n equals to 0 to infinity, n plus 2, and then n plus 1, a sub n plus 2, x minus x naught n. So now what you did is just shifting the index from n minus 2 to just n, and from n starting from at 2, now n starting at 0. Okay, so that is the long cut of doing stuff. So the shortcut of doing stuff is that, so look at this original series here that you haven't shifted, okay? So now your goal is to make n starting from 0, so you want to minus 2 with, you want to reduce it to 0. So the shortcut is that for the, what do you call here? When you minus this with 0, you have to add up here everything with, when you minus 2, everything here must add 2. Okay, so the shortcut is that, okay, so now you want your n to start from 0. So it's 0. But up there inside the summation term, n plus 2, you have to add 2. Okay, so that everything balances out. A n plus 2, x minus x naught, n minus 2 plus 2 is just n. Okay, so now when you expand this series, then you will get this. So starting from n equals to 0, so 0 plus 2 is 2, 0 plus 1 is 1, so just 1, and a sub of 0 plus 2 is a2, x minus x naught to the power of 0 is just 1, so you just end up with the first term is 2a2, and then you expand, this is when n equals to 1, and this is when n equals to 2, okay, and so on and so on. So this is about shifting the summation index. And yeah, so why do we want to shift the index? Because you see, when we write the sum of two series, so in this case, you have two series both starting at different point. You want to start both series at the same value of the index. Okay, so you want to say, and you want it to start at the same value of n, so that you can combine the series and make your life easier. Okay, so that's why we want to, shift the index of the summation. So let's look at this example. So here, say you have this particular example here. I just need some space here. Okay. Right. So now, originally, you have this series, your n it starts with n equals to 2, and here starts with n equals to 1, and you look at the indices of x are different, so you can't add them and combine them into a single series. So what you do is you put this x squared inside of the summation term. So when you put that, then it becomes x to the power of n minus 2 now plus 2, then you just get x to the n. But you haven't changed anything at the bottom here. You're just putting the x squared inside the term. And this one also, you can put it inside. So you get 2n times a sub n. Okay, and then we want to make the starting point of the series the same. Okay, so now, okay, let's do this separately for each series. So here, is n. So now we want to so this is, okay, let it be s here, but here we want to change from n minus 1 to just n, or anything, just not with the minus 1. It can be just n, just s, anything. So let's say you put s equals to n, so just change all these n to s. So you have s, and then as times x to the power of s. But now you want to change here this to become s. So you the long cut is you substitute s equal to n minus 1, or you can also do the shortcut, i.e. at the bottom here you minus 1, so at the top here everything must plus 1. Okay, so here the n become n plus 1, and then the a sub n becomes a sub n plus 1. Okay, a sub n plus 1. And then the top here, when you plus 1, it just becomes n. Okay, so then you will end up with the series starting from and or s, I mean starting from 0 to just maintain 2, because 2 is just a constant. Okay, so you don't have to add another plus 1 there. So instead of n, you have s plus 1, and instead of a sub n, you have a sub s plus 1 or n plus 1, anything, and then x to the power of just n or just s. So now you have, you know, slowly making things in order. And next you want to make the series starting at the same point. Okay, so starting from here, so now you can just, okay, in this particular example, for this particular series, you can just replace it by s equal to 0. Why is that? Okay, so why is that? So let's see. Okay. Okay, so I'm just showing you that in this particular example, the first term here, so let's look at the first term. So this first series, okay? So starting from s equal to 2, you have 2 times 2 minus 1 times a of 2 x squared. Supposedly you start from s equals to 2 and then 3 and 4 and so on, right? So you have 2 times 1 is just 2, and then a2 x squared and so on and so on. But what if you start this series from s equals to 0? So you have 0 times 0 minus 1 times a0 x 0. So everything here will become 0, because 0 times anything is just 0. And then plus, what if you put s plus equals to 1? Because when you start something at 0, then you will have to, 0, 1, 2, and so on and so on. So when s equals to 1, you have 1 times 1 minus 1, a1, and x1. So this term also, because 1 minus 1 is 0, so everything will become 0. And then when s equals to 2, you have this term here, 2a2 x squared, and so on and so on. So in this particular example, the first term here, it doesn't matter if you start it from 0. You don't really have to shift anything, because even if it starts from 0, you will still start the series with 2a2 x squared. So that's why in this particular example, s equals to 2 can just be replaced by s equal to 0, so that the combined series becomes, so when you just put this one equals to 0, you don't need to do anything. So you just combine the series, so starting from s equals to 0, and then you factor out the xs here, and then you just put in all the coefficient in front, okay, just factorize. And then this will become the combined series, and from here you can start to expand if you like, okay. So you can expand from s equals to 0, you will get this, and then s equals to 1, you get this, s equals to 2, you get this, and 3, and so on and so on. Okay, so that's about the shifting summation index in the power series. All right, okay. Okay, next is to look at the theorem on the existence of power series solution for an ordinary differential equation, ODE. So let's say if you are given an ODE, if the functions p, q, and r in the differential equation here, so you recognize this as an ODE, right? So y double prime times p of x times p of x times y prime plus q of x times y equals to rx. So here, let's say if this the function p, q, and r are analytic at x equals to x naught, then every solution yx of the equation 4 is analytic also at x equals to x naught, and thus can be represented by a power series in the powers x minus x naught with the radians of convergence are greater than 0. So don't worry about these terms. It's just mathematical terms defining what works and what not. So meaning, let's say you have this ODE, and then you want to propose this power series y as a solution to the ODE, okay? Okay, but now you have to make sure that all these P, Q, R are analytic at the value of x equals to x naught. So what do you mean by analytic function? So the definition, the mathematical definition of analytic function is this. A function fx is called analytic at x equals to a if the Taylor series for f of x about x of equals to a has a positive radius of convergence and converges to f of x. So this is the mathematical definition of how do you define whether the function is analytic or not at a given value, meaning it can be defined at a given value. So let's recap what is Taylor series. So this is a Taylor series function. So if f of x is an infinitely differentiable function, meaning infinitely differentiable, meaning you can get the first derivative, the second derivative, the third derivative, infinite. You can get the different derivatives of the function infinitely. You can even get the 1000th derivative of the function. So if fx is an infinitely differentiable function, then the Taylor series of f of x about x equals to x naught is this. Okay, so this is the Taylor series of fx, given that fx is infinitely differentiable and you have to know the value of x naught. Okay, so f of 0, so when n equals to 0, f0 is just fx. Okay, so fn is not to the power of something, but rather the nth derivative of x. So if you have the f bracket 4 of x, meaning the fourth derivative of the function x. And there's this also a term on Maclaurin series. Okay, so it's like Taylor series, but Maclaurin series, in Maclaurin series, the value of x naught is equals to 0. So in general, given this power series solution, this is Taylor series, but when x naught equals to 0, then it is actually Maclaurin series, although it's not wrong to say that it is also a Taylor series at x naught equals to 0. Okay, yeah, so let's do an example, quick example 2. Okay, so let's find the power series form, the series form of the following function. So here, this because these are all reviews of Taylor series and Maclaurin series. So we want to find the series form of the following functions: e to the exponential of x squared. The second one is ex plus sine x, and the third one is product of ex times cos x. So you can scan the QR codes here to see the derivation of Maclaurin series for cos x, sin x, and exponential of x respectively. And then you will see that you will get the, let me show you the example just now. The familiar examples here. So for e to the x, you will get something like this. Okay, so when e to the x squared, you will get from n equals to 0 to n x squared and n times. So it's just substituting the exponent into the power series. Okay, then you can further expand it, of course. But what I mean is that if you want to find out where you get this series form of the respective functions, ex, cos x, and sin x, and from the ex you can find out ex squared, then you can watch the video by scanning the QR code here. Okay, and then you will get the respective function. So here you can look at your notes at page, which page is this? 140. Okay. Let's do a quick example here. So here EX squared. So for EX squared, the Taylor series for generally for any exponential just x, you will know that from the derivation, if you watch from m equals to 0 to infinity, then you will get x to the power of m over m factorial. But then now you have x squared, so you just put instead of x, you just put x squared here to the power of m. Then you can expand it. So when you expand this from m equals to 0, so x squared to the power of 0, 0 factorial, plus x squared to the power of 1, 1 factorial, plus x squared to the power of 2, 2 factorial. I'm going to stop at 3. You can go on if you want, and so on and so on. So here you get 1 plus x squared plus x to the 4 over 2 plus x to the 6 over 6, and so on if you like. So this is you know, the series form of the function e to the x squared. And next thing is the second one is ex plus sin x. So from ex, you know, the series form of ex is from m equals to 0 to infinity, x to the power of m over m factorial. And for sin x, the series form is from m equals to 0 to infinity, negative 1 m multiply with x to the power of 2m plus 1 divided by 2m plus 1 factorial. So when you add this ex plus sin x, so basically you're just adding the two series. So you add this series plus from m equals to 0 to infinity, negative 1 and then you can expand them from m equals to 0 until m infinity. So you do this separately. So do the first one here first. So you get 1 plus x squared over 2 plus x cubed over 3 factorial, and so on and so on. And then plus with the second part of the series, which is x minus x3 over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial, and so on and so on. And you can combine them as if necessary. So you get 1 plus 2x plus x squared over 2 factorial. I'm really sorry about this, you know, the discontinuity of the marker in the whiteboard here. Just bear with me, yeah. And so on and so on. You get the idea. So the third part of the example, you can try to do it on your own because it's a multiplication. Okay, so the third example is e to the x times cos x. So now here is the multiplication of the series. So from the from this video, you can learn how to get the series form of cos x, or you can simply look at the earlier part of the slides to get what is the series form of the cos x. So this whole thing here multiplied with this whole thing here, and you can expand if you like, and you can refer to the solution in your notes at page 141. Okay. Right, so we'll break here before we continue to the next part of the video where we will use power series method to actually solve the differential equation. Okay, thank you.